Good afternoon, everyone. This is lecture number 34 for IC242, Continuum Mechanics. And today we'll be talking about the application of continuum mechanics to fluid flows. So till now, in the previous two lectures, we talked about constitutive modeling, and we talked about what's the motivation behind constitutive modeling, in the sense that mathematically the equations that we developed, the conservation equations, are not closed until we provide some sort of material properties to the mathematical system, which ultimately closes the system so that we can solve the modeling equations to predict the deformation in solids or the rate of deformation typically in fluids. Uh, in the previous lecture, particularly, we talked about the constitutive modeling for linear fluids, as you can see. So let's do a quick recap from of the previous lecture. So we talked about what fluids are. We started with fluid statics, and then finally we moved to the dynamics of fluids, which was the main topic of discussion for previous lecture. As I said that we started with we started with an isotropic assumption. So we assumed that the fluid is isotropic as well as linear. So this assumption here, so this expression here shows us that the fluid is linear. Sorry, not this one. This one, tau ij is k ij kl dkl. So that shows that the shear stress tau is linearly related to the rate of deformation tensor dkl. And next, we applied the assumption of the fluid being isotropic. So in that case, we got an expression with the two Lamick constants as we got for the solids in the previous lecture. And these lambda star and mu star were called the viscosity coefficients. So we saw that we need to provide two fluid properties to be able to characterize the fluid completely. And then further, we applied the Stokes hypothesis, which says that the mechanical pressure is the same as thermodynamic pressure unless you have some sort of expansion damping happening in the fluids, which is extremely rare unless you are dealing with high frequency waves in shocks. So finally, we reduced the number of viscosity coefficients to one, which we called mu star, which is also known as the dynamic viscosity of the fluid. So what we saw was that under the assumption of linear fluids with the isotropic fluids, assumption applied as well, and finally the Stokes hypothesis, when it's applied, we are left with only one constitutive property, or the rheological property of fluid, called its dynamic viscosity mu star. I mean, they are used interchangeably. So we got the final expression for the shear stress tau as a function of our rate of strain tensor Dij, which is written in this boxed equation at the bottom. So what we did was we substituted this expression, which is the constitutive model for the fluids, into the conservation equations. Not taking isothermal fluid, that is, there's no change in temperature or the internal energy of the fluid. So we finally had 5 equations. The first one being the conservation of mass, the equation number B being the conservation of momentum, equation number C giving us a relation between the stress tensor sigma and the rate of deformation Dij. The fifth equation giving us a relation between the rate of deformation tensor Dij and the velocity field V. And finally, the equation number E gives us the relation between pressure and density, which can be obtained using an ideal gas law for gases. And using this, we saw that we had finally closed the mathematical system. That is, we had an equal number of unknowns and the number of equations. So finally, we were confident that we can solve this equation. So what we did next was that we substituted a couple of equations to further reduce the number of equations to 2 out of these 5, which the first one being the same as the conservation of mass equation, and the second one, the conservation of momentum equation, was simplified to the Navier-Stokes equation, which is the boxed equation here, which gives us a relation between the acceleration, which is the time rate change of the material derivative of the velocity field, in terms of the pressure gradient, body forces, the body force vector Bi, the diffusion term, which is the second order gradient of velocity, and the viscosity mu, and the density rho. So this is called the Navier-Stokes equation, which, when solved in conjunction with the conservation of mass equation, can help us find the velocity and pressure in the flow, which are the two quantities which we need to know to be able to characterize the flow field completely. Okay, so pressure typically is used in engineering to calculate the forces acting on objects. For example, if you have an aeroplane wing with flow happening around it, you would want to know what sort of forces are acting on the wing. So the pressure helps you calculate the form drag acting on the wings, and then the velocity field typically helps us calculate the shear drag or the friction drag on the wing. So that helps us calculate the total drag on the solid object or the wing, in this case, aeroplane wing in this case, inside the flow field. Okay, so pressure and velocity help us. If you know about these fields, we have characterized the flow completely. So under the effect of external stress field and body forces, we have to calculate the evolution of our pressure and velocity fields. So that typically is what the aim of continuum mechanics, what the use of continuum mechanics is. So in today's lecture, I will show you the application of these equations that we have developed in the previous lecture. We will solve them for a particular situation and show that we can indeed obtain the pressure and velocity field using these equations that we have developed. That is the conservation of mass equation and the Navier-Stokes equation, which is nothing but the conservation of momentum equation. Okay, and beware that the system that we are solving today is a very special and very it's a very special case for which the analytical or the closed form solution exists. Now, for most of the situations that we deal with in engineering or in nature, the solution, the closed form or the analytical solutions to these equations do not exist, and we have to use advanced numerical techniques to obtain solutions of these equations in the numerical discretized form. But nevertheless, today's lecture is simply showing you an application of this to a real situation and showing that and impressing upon us that yes, we can actually solve these equations and obtain solutions which are useful. All right, but before we start with that, we start with the final equations. We start with the application case. Let's talk about a few special cases which are quite general in the sense that we do encounter them and we do use these modeling assumptions for many fluid flow situations, which also included today's example. Okay, so let's write the conservation of mass and momentum equations so that we can refer to them easily. So the conservation of mass equation. Right, so let's check with the form that we obtained last time, and it does match with the equation that we obtained in the previous lecture. All right, so these are the two equations that we'll be using to solve today's application problem. So let's talk about a few special cases before that. So the first special case is incompressible flow or incompressible fluid. Incompressible fluid. So that means that the fluid is incompressible. For example, water. So that means if you put water in a box and apply pressure to it, then the density will not change for this fluid, for water in this case. So, of course, nothing is purely incompressible. We do see there's some amount of compression in the fluid or the liquid obtained or water obtained when we apply external pressure. But it's an assumption that we are using here that the fluid is incompressible. So that would mean that the density is constant. So if the density is constant, then equation number one, which is the conservation of mass equation, rho dot term becomes zero. So what we obtain is one reduces to the velocity field is solenoidal, or what that means is the divergence of velocity, or vi comma I is zero. Okay, so that's a simplified form of the conservation of mass equation. And the conservation of momentum equation stays as it is except the last term. So let's write that. So you will see that the last term, I have written it as the del by del xi of vk comma k. Okay, so that's typically how we can write a second order derivative as the first order derivative of a first order derivative. So and we already have seen that vi comma I is zero. So k comma k is the same thing. That's zero. So that means this term is zero. Because v k comma k is 0. Right. So this for this case of a incompressible fluid, these are the simplified forms of the mass and momentum conservation equations. Right. So the second special case that I'll introduce to you is for frictionless or inviscid fluids. Okay, so what that means is that the fluid provides no friction or no viscosity. So we saw that mu is for the case that we developed, mu was the only viscous coefficient we had, and if the fluid is if the fluid is inviscid or frictionless, then the viscosity is zero. So that means that the fluid provides no resistance. As I said that, for example, if you have a glass full of honey and you try to stir a spoon into it, then you will experience some sort of friction, some sort of resistance to that stirring, which will be much more as compared to what you would experience if you try to stir a glass full of water, because the viscosity of honey is more than the viscosity of water. But if the viscosity is zero, that means that the fluid does not provide any friction or resistance. In fact, such fluids are called ideal fluids. Okay, ideal in the sense that they flow freely. So fluids, the word fluid came from the idea that it flows freely. It does not provide resistance, but we know that the fluids do provide resistance. But an ideal fluid is one which provides zero resistance. Okay, so there's no real fluid as such that provides exactly zero resistance, but that's one way to mathematically model these ideal fluids. That is, an ideal fluid is one which has zero viscosity, that is mu equals zero. So for this case, the continuity equation remains as it is, or the conservation of mass equation remains as it is, but the momentum equation gets simplified because all the terms that had a viscosity in it are gone. So we are left with only the left hand side, which is the acceleration. And the right hand side simply has the body force as well as the pressure gradient in it. So for an inviscid or a frictionless fluid, let's say you have frictionless fluid inside a pipe, then the only thing accelerating a pipe is either body force, that is gravity. So if the pipe is kept at an incline, then the gravity will accelerate the flow, and or the pressure gradient. So if you apply a pump, which basically provides a pressure gradient and the pressure difference between the two ends of the pipe, then the water will also start flowing or accelerating in this case. And there is no term that's slowing down the acceleration, because the viscosity is zero, right? And these equations, this set of equations have a name. It's called Euler equation. So the Navier-Stokes equation simplifies to Euler equation under the assumption of an ideal fluid. That's all we talk about this. There's plenty of stuff we can talk about Euler equation, but that's beyond the scope of today's discussion. I'm sure if you take an advanced course in fluid mechanics, you will definitely learn about these things in much more detail. All right, the next special classes or this in the next special case that we can have is a steady flow. So the word steady means that things do not change with time. Okay, that's called a steady flow or a steady state flow. So what that means is that the velocity field, which we're talking about, is not a function of time at all. That means the time derivative of velocity, the partial derivative of velocity with respect to time is zero. Okay, so the velocity at any given point in space does not change with time. Remember, it's not the material derivative we're talking about. We're talking about the partial derivative of velocity with respect to time. So in the room coordinates, if you fix a coordinate, then the velocity field will not change with time. It's like you make a change in the flow, you make a change in the conditions in the pipe, and then you wait for some time, and then finally you will see that the flow will stop changing. So the effect of the change initially has you've given enough time for the flow to develop, and now it's reached a state that is the velocity field does not change with time. Okay, that's again a very common situation that we experience, and we'll be using that for today's application case as well. And the fourth and the final one, which we'll be discussing today for as a special case, is called irrotational flow. Right. So if you remember, many lectures ago, we talked about the velocity gradient tensor, that is L. So L can be split into two parts. One is a symmetric part, which was the rate of deformation tensor, and the other was a skew symmetric part, which which we called as the vorticity or a spin tensor. Okay, that we named as W. So if that W is zero, then we say that the flow is irrotational. That is, there is no rotation in the flow at all. Okay, so we discussed in some detail as to the physical interpretation of what this W is. So these special classes of flows are called irrotational flows, where W is identically zero everywhere. If you remember that we discussed that W is a skew symmetric tensor, so it has only three distinct components. So from these three distinct components, we can create a vector, which we call the axial or the dual vector of W, which was named as omega, called the vorticity or the vorticity vector. So the vorticity vector, which we defined as half of the curl of velocity. Okay, this has been discussed previously. So if your flow is irrotational, that is W is zero, that means omega is also zero. That means the curl of velocity is also zero. Okay, so if the curl of velocity is zero, then we can simply write this as curl of velocity is zero. And we already know the identity that the curl of the gradient of any scalar field, sorry, is always 0. Okay, so we have discussed this. I think we discussed this in the beginning of the course when we talked about tensor calculus. So we talked about this identity. So the curl of the gradient of any scalar field is identically 0. So if you have the curl of velocity being 0, so that means you can write your velocity as the gradient of some scalar field. And these classes of flow are called potential flow. Okay, the word potential comes from the sense that the velocity is the velocity vector field is because of a difference in phi at two points, adjacent points. So that's the meaning of gradient. That's del phi by del x1 e1 plus del phi by del x2. So if you have phi scalar field changing, so it's not a homogeneous field, then that would mean that there is some gradient of phi, and that is what velocity is at any given point. Okay, so there's a potential of phi that causes so that phi change, the difference in that phi potential causes a velocity to exist at any given point. Okay, so this is called potential flow. It's again a very common special case which we do talk about in many fluid flow situations. Again, I won't go into those details because that's not in the scope of today's lecture. So let's quickly jump to the application problem that we've been looking forward to. So this is a solved example in the book. It's example 741. So you have an inclined surface. You could think of that as a mountain slope, and the inclination is beta. And then you have water. Let's use a different color. Blue is a good color for water. So we have water flowing above this inclined surface, and the height of this water layer that's flowing above the incline is h. The pressure on the surface is P naught. That's the atmospheric pressure. So if you have a river flowing on a mountain, then the pressure at the top is nothing but the atmospheric pressure, the pressure applied by the atmosphere. Okay, so this is what's happening, and it's given to us that the fluid is incompressible. Okay, again, a decent assumption or a decent condition because it's water and water is incompressible. The fluid is Newtonian. Okay, again, a decent assumption because water is considered Newtonian. So it's an incompressible Newtonian fluid in a steady flow. Okay. So remember, we talked about the flow being steady means that del Vi by del T is 0. Okay, that's the situation. So that means that if you keep watching this water flowing for a long time, then you take any point in space where you have water molecules around, then you would see that the velocity at that point in space will not change with time. Okay, so that's steady flow. And the water is flowing under the action of gravity. So the incompressible, so this incompressible Newtonian fluid in a steady flow under the action of gravity. So you have, that's the direction of the gravity vector. Now, again, very common. So if you have a mountain slope, then the water flows down because of gravity indeed. So this is down an inclined slope of angle beta. Okay, so that's what's given to us. Now, what do we have to do? We have to determine the pressure and velocity in the flow. All right. So as I said that pressure and velocity are the two fields you typically need to be able to utilize or to be able to characterize the flow field completely. So that's what we have to find. So our job now is to utilize the Navier-Stokes equation and the conservation of mass equation to solve for the pressure and velocity everywhere in this flow situation. Right. So the first thing we have to do is like decide on a coordinate system, because we'll be writing pressure and velocity as a function of x1, x2, and x3. So first we have to decide what coordinate system we have to take, because the physical situation there's no coordinate system attached to it. Coordinate system is our choice when we are solving the problem. So in this case, it's extremely convenient if we choose a coordinate system which is along the direction of the inclination or the slope. So we call that x2, and the direction which is perpendicular normal to the inclined surface, that we call x3. So that means that x1 is coming out of the plane of this sheet. All right. So this is the coordinate system that we'll be working with today. Now, when we say that we need to find the velocity field, that means we have to find v1, v2, and v3, which are the three components of velocity in this coordinate in the coordinate direction that we have decided. Now, first, we will assume that v1 is 0. What that means is that I mean this is easily I mean you can easily find that from the symmetry of the problem. So if you have a fluid flowing down an incline like this, then you won't see the fluid moving either outside the plane of this sheet, because it will tend to flow in the direction of x2 only. Again, you won't see fluid going up or down in this case as well. So from the symmetry of and the physical situation that's given to us, we can easily see that v1 is equal to v3 is equal to 0. Okay, so what that means is that we only have a flow in the x2 direction. That is, v2 is the only component of velocity that exists, and also that v2 is a function of x2 and x3 only. Okay, so the velocity in the x2 direction does not depend on the x1 direction. Again, because of the symmetry of the geometrical symmetry of the problem, it won't come out of the plane or inside the plane of the paper. It will simply flow down the incline, and it may change depending on the height from the base of the plane. So that's applying the symmetry. We call it, say, using symmetry and physics. Okay, symmetry in the sense that the coordinate directions, and physics in the sense that the direction of gravity. If the direction of gravity was different, you may have seen that if the direction of gravity was coming out of the sheet of the plane of paper, then you would definitely see that the situation would be much different. So it depends on the direction of gravity, that's the physics, and the symmetry, which is the coordinate system, that the way we have chosen it. Okay. And then pressure, again, as we'll see, will only be a function of x2. We expect the pressure to change as the flow goes further down the incline. pressure could also be a function of x3. So we would expect the pressure to change as we go away from the surface of the incline. But again, because of the symmetry, we don't expect the pressure to be a function of x1 because I mean we can assume that it's a very wide mountain and we're talking about situation that's happening somewhere in the middle of the flow. Okay, so this is from symmetry. So if you want to visualize in 3D, so you have an incline like this. So this is your surface and the flow is flowing over like this. Okay, so this is your so this direction is your x1 direction. So if you're talking about flow happening in this region, then we don't expect the pressure to change because it's a very wide flow situation. So there's no reason for the pressure to be a function of x1 coordinate. All right, so we already have, using the ideas of symmetry and physics and intuition, we have simplified the number of variables we need to find. All right, so let's start. Now, let's quickly go back and see what assumptions we can apply in the form of special cases. So the first special case was incompressible fluid, and that is indeed true for this situation as well. So that means that the conservation of mass equation simply is Vi comma I is equal to 0. So we can apply that for this problem as well. So we have Vi comma I is equal to 0. That's because the flow is incompressible fluid. Okay, so Vi comma I means when we expand this, this becomes V1 comma 1 plus V2 comma 2 plus V3 comma 3 is 0. Right. But we already saw that V1 and V3 are 0. So that automatically gets rid of the first and the third term. So it's only V2, which is a function of x2 and x3. So since these two are 0, so we have del V2 by del x2, that is 0. I just wrote that in the del by del x2 form. And from this, if you integrate both sides, what you get is V2 is equal to a function of x1 plus some constant. All right. There's no x2 here because if we had an x2, then del v2 by del x2 would not be 0. So v2 can only be a function of x1, x2, and constant. And moreover, x3 is not allowed because we already saw in the previous lecture, in the previous slide, that v2 is only a function of x2 and x3, as we can see from here. So the underlying constraint and the mathematical situation, the mathematical constraint here gives us that v2 is only a function of x1. V2 should be a function of x3. That's what I showed in the third slide. So let's have a look again. So there's a question that should V2 not be a function of x3? Did I say x3? Okay. Sorry. Yeah, I'm sorry for that. So it should be x3. Thanks for the correction. I think I've been talking about the coordinates incorrectly. So in the third slide, we saw that V2 is only a function of x2 and x3, not x1. And this del V2 by del x2 equal to 0 means that V2 cannot be a function of x2, so it is only a function of x3. Okay, we won't write the constant that's absorbed in the function of x3 here. So we simply say that V2 is simply a function of x3. So the conservation of mass equation helped us simplify the constraint that V2 is only a function of x3. Okay, so physically, what we see is that the component of velocity down the incline is only a function of x3. It's only a function of the distance it has from the surface of the incline. So water which is very close to the surface may be either flowing slower or faster than the water on the surface of the flow. But we have an intuition that the water at the bottom of the incline is flowing much slower as compared to water at the surface. That's what we typically see in rivers, etc. as well, that the flow rate at the near the bottom is very slow, and as you go up you see that the water flows very fast. Okay, again, that's one of the reasons. If you think of windmills, you have windmills which are installed at a very the windmills have a very long height of the pole, so they tend to stay away from the surface because the surface slows down the flow. It provides resistance, and hence the flow speed at the bottom or the ground level of air is much smaller than the flow speed at a distance very far away in the air, and that's the reason you feel very high winds if you stand on the top of very tall buildings. Okay, so again in water we see that we haven't seen that yet. In this case we are just developing an intuition that it may come out that the velocity v2 component is very large on the surface or and very small at the bottom. But it definitely is seen from this equation in front of you that v2 is only a function of x3. All right, so now next, before we apply the conservation of a mass equation, let's write the rate of deformation tensor and its definition. So rate of deformation tensor was the symmetric part of the velocity gradient tensor, that's vi comma j, that we called lij earlier. So in this case, we have now dij is symmetric, so we have 6 distinct components here. So let's see what they are. So d11 is half v1 comma 1, so we basically have v1 comma 1, which is 0 because v1 is 0. d2 is v2 comma 2, which also is 0 because that's written on the second line from the top. v2 comma 2 is 0. d33 is v3 comma 3, which again is 0 because v3 is 0. Then d12 is half v1 comma 2 plus v2 comma 1. Sorry, it's not 0. So v1 comma 2 is 0 because v1 is 0. And in fact, v2 comma 1 is also 0 because v2 is only a function of x3. So this indeed is 0. Then we have d23. That's going to be half v2 comma 3 plus v3 comma 2. Now v2 comma 3 is definitely not 0 because v2 is a function of x3. So that remains as it is. But v3 comma 2 is 0 because v3 is 0. So what we see is that d23 is v2 comma 3 by 2. And then d13 is half v1 comma 3 plus v3 comma 1. Again, this is 0 because v1 and v3 both are 0. So what we see is that in the complete d, or the rate of deformation tensor, we only have d23 and d32, which is the same as d23, as non-zero. So let's write that. So let's write our d tensor. The diagonal components are 0, and then d23, which is this third column in the second row, is v2 comma 3 by 2, and then d32 is also v2 comma 3 by 2, and the rest of the terms are 0. So this is our rate of deformation tensor Dij. All right. So the next step is to write sigma ij. So sigma ij, if you remember, was written as, using the constitutive law we had, was written as minus p delta ij plus 2 times mu times dij minus 2 by 3 times mu times dkk. Let's quickly confirm that. So the equation number C is what I've written. So sigma ij was minus p delta ij plus 2 mu dij minus 2 by 3 mu times delta ij times dkk. Of course, we need to have a delta ij here because otherwise uh, we don't have the same dimensions of tensors. All right. Now dkk is 0 because if you see the d tensor in front of you, then the trace of that d tensor is 0. So this dkk term is 0. So what we are left with is sigma ij is minus p times delta ij plus 2 mu dij. So let's write the sigma tensor. So sigma 1 1 is simply minus p because d11 is 0. So then the rest is all 0, and the sigma 2 2 is again minus p. Sigma 3 3 is also minus p, and then sigma 2 3 will become mu times v2 comma 3, and this becomes mu times v2 comma 3. Right. So that is our sigma tensor. So what we've done is we have written the tensorial form of sigma using our rate of deformation tensor, which is written in terms of the velocity. Now we are in a position to apply the conservation of momentum equation, or the Navier-Stokes equation. So the momentum equation is sigma I j comma j. That's the surface forces. Then you have rho times bi. That's the body force. Oh, before that we have to write the body force as well. I'm sorry. So let's write the body force. Now the body force in this case is gravity, and the body force vector bi is simply, if you go back to the picture here, then gravity has a component in the x2 direction and x3 direction. In fact, we can see that the gravity component in the x2 direction is simply the sine of beta, because if beta was 0, then the component of gravity in the x2 direction would have been 0. So it's a sine beta component, and the gravity component in the x3 direction is a minus cos beta, the minus being because it's in the opposite direction of x3. So I can write the body force vector as, and remember, body force was, B is a body force per unit mass. And since we know that the force is m times g, so the body force per unit mass is simply gravity. So it's the component of gravity g sine theta in the x2 direction, and minus g cos theta, sorry, beta of theta, minus g cos beta in the E3 direction. So that's our body force vector here. All right, so now we are in a position to apply the momentum equation. So that's sigma ij comma j plus rho bi is equal to rho times vi dot. Okay. Now rho times vi dot can be written as del vi by del t plus vk vi comma k. That's definition of material derivative. Now we already know that it's a steady flow situation. So that means del vi by del t is 0. So this is 0. So what we have finally is sigma ij comma j plus rho bi is rho times vk vi comma k. So this is our momentum equation. Now what we can see here is that it has one free index, that is I. That makes sense because the momentum equation is for the momentum balance, which has three components. It's a vector. So we have three equations here. So we have the component which is I equal to 1. So let's apply that. So we get sigma 1j comma j plus rho b1 equals rho bk v1 comma k. All right. So in this case, it's sigma 1j comma j. So this term this term will expand. So we get sigma 1 comma 1 plus sigma 1 2 comma 2 plus sigma 1 3 comma 3 plus rho b1 equals rho v1 times v1 comma 1 All right. So let's go back and have a look at the sigma terms. Sigma 1 comma 1. Now sigma 1 is nothing but minus p. So sigma 1 comma 1 becomes minus p comma 1. We write that. And then sigma 1 2 and sigma 1 3 are both 0. So then that gives us two zeros. And then the body force also has no component in E1 direction. That means B1 is also 0. And then V1 and V3 are 0. So the first and the third term on the right hand side are 0. And the second term, which is V2 times V1 comma 2, is also 0 because V1 comma 2 is 0. So we have a 0 on the right hand side as well. So this the E1 direction momentum equation simply boils down to minus p comma 1 is 0. So this we'll call as 1. Okay, so before we utilize that, let's write the momentum equation for I equal to 2 as well. That becomes sigma 2j comma j plus rho b2 is equal to rho pk v2 comma k. Okay. Now let's do things in a more compact form this time. So sigma 2j comma j has three terms: sigma 21 comma 1, sigma 22 comma 2, and sigma 23 comma 3. Now this talks about the second row. So sigma 21 comma 1 is 0 because sigma 21 is 0. Let's call it a 0. And then sigma 22 comma 2. So the sigma 22 is minus p. So that becomes minus p comma 2. And then we have sigma 23 comma 3. which is mu times v2 comma 3. So that becomes mu times v2 comma 3 3. And then rho b2. Now rho b2 is nothing but g sine beta. So this becomes plus rho g sine beta. And then the right hand side is rho times v1 times v2 comma 1, which is 0 because v1 is 0. The second term is v2 times v2 comma 2. Now we also know that v2 comma 2 is 0 because v2 was only a function of x3, so that's 0 as well. And the third term is v3 times v2 comma 3, which is 0 because v3 is also 0. It's the right hand side again now simply becomes 0. So this is our equation number 2. Similarly, we apply this for I equal to 3 the same way. This becomes sigma 3j comma sigma 3j comma j plus rho b3 is equal to rho times vk times v3 comma k. Okay, so this is our equation, momentum equation for I equal to 3. Now sigma 3j comma j, let's see the third row of sigma. So sigma 31 comma 1 is 0. Sigma 32 comma 2 is mu times v2 comma 32. This becomes, and then the next term we have is minus p comma 3, which comes from the sigma 33 comma 3. Sigma 33 is minus p, that becomes minus p comma 3. And then b3 is nothing but g cos beta. Okay. And the right hand side again is 0 because v1 and v3 are 0, so that becomes 1. First and third term are 0, and the second term is v2 times v3 comma 2, and v3 is also 0, so v3 comma 2 is 0 as well. So this is our third equation here, but the first term on the left hand side is also 0 because we can write this as v2 comma 2 3 because of the symmetry of the second order derivative, and this can then be written as v2 comma 2 and comma 3, and we already know that v2 comma 2 is 0, so that means that so this is 0, so we get minus p comma 3 minus rho g cos beta is 0, and that's equation number 3. Okay, so we have successfully written the 3 momentum equations in a simplified form. So the way we'll start is we'll first calculate the pressure field. So it's easiest to see that we can calculate the pressure field from equation number 3. So we'll integrate that. So we integrate 3. So what we get is del p by del x3 is equal to minus rho g cos beta. So if you integrate that, what you get is p is minus rho g cos beta times x3 plus some function of x1 and x2. But remember a couple of when we started solving the problem through the symmetry, we said that pressure is only a function of x2 and x3. So that means the dependence of the constant on x1 is not there. So f is only a function of x2. All right, so this is the pressure. Now, to be able to get this function f, we have to apply some sort of boundary condition. And one boundary condition that was given to us was that P was equal to P naught, at atmospheric pressure, at x3 equals to h. Okay. So at the surface of the flow, P was equal to P naught. Let me show you the figure so that you can recall. So we can see that the pressure is equal to P naught on the surface of this flow. So the surface of the flow is has a coordinate x3 equal to h. So we apply this condition, and that will give us the constant. So we can say use. So we get P naught is equal to minus rho g cos beta times h. So basically our f x2 is P naught plus rho g cos beta times h. Okay, so f as a function of x2 actually is not a function of x2. It's only a function of P naught and h. All right, so let's substitute this into the expression for pressure because this is a boundary condition that we applied. So finally, we have P is equal to minus rho g cos beta times x3 plus, and f is nothing but P naught plus rho g cos h. So we can combine the terms of rho g cos beta. So we have P equal to P naught plus rho g cos beta times h minus. So that's the expression for pressure. Now, let's try to understand this intuitively. So at the surface, of the flow, which is x3 equals h. If we substitute that x3 equal to h, we get P equals P naught, which is fine. And as you go down towards the bottom, we have a hydrostatic component. So the pressure increases as you go down in a water pool. In this case, the gravity only has a component along that direction of x3. So we see that the pressure actually increases because h minus x3 is a positive term as x3 becomes less than h. So as you go deeper and deeper inside the water flow, what you see is that P becomes greater than P naught, which is what we expect as you would see in a pool. As you go down in the pool, there's a hydrostatic component which provides pressure as you go deep into the pool. So the pressure increases as you go down into the pool. Okay, so this is what the pressure field is for this situation as a function of x3. So we see that pressure is only a function of x3 here, not a function of x2 at all. All right, so that's all for the pressure. The second problem was to solve for the velocity. So for that, we will use equation number 2, which is given at the bottom of the page. So minus p comma 2 plus mu v2x33 and g sine beta is equal to 0. So let's rewrite that. So we'll say integrating 2. So equation number 2, let's write that first. So minus p comma 2 plus mu v2 comma 33. Check that. And then plus rho g sine beta. This is 0. So let's integrate that. So we have v2 comma 33 as p comma 2 by mu minus So when we integrate that the first time, we get v2 comma 3, and this is equal to sorry. So let's see what v2 was. So v2 was only a function of x3. Okay, so that is what we saw when we applied the conservation of mass equation. So if v2 is only a function of x3, then we do not have a constant in terms of x1 or x2, but we do have some constant, let's say a here. Okay, so we can check, we can differentiate that with respect to x3, and we will get p2 comma mu and minus rho g comma mu times sine beta. So we can integrate that again. So we get v2, and then we have 1 by mu p comma 2, but wait, so p comma 2 actually is 0, because we just have found that pressure is not a function of x2, so we don't really need to write p comma 2 here. We can actually remove that, so we can simply say that p comma 2 is 0. We just saw that, so let's remove this term. So v2 becomes minus rho g comma mu minus rho g by mu times sine beta, and then we have x3 square by 2, and then we have plus ax plus another constant, which is b. Okay, so that's sorry, ax2 x3, sorry, plus b. So that's your v2 as a function of x3. Now again, you see that you have two constants of integration, that is a and b, that you have to find, and for that we will need some sort of boundary condition here. Now one boundary condition that we can apply for velocity is something called a no slip condition. Again, you may not know about it, but I just talked about this, that as you go closer and closer to the inclined solid body, then the flow becomes slower and slower. In fact, the flow at the point touching the inclined surface, that is at x3 equal to 0, is 0. So that's called a no slip condition. So boundary conditions. So v2 is equal to 0 at x3 equal to 0. That's called a no slip condition. So the flow which is touching the inclined surface on which it is flowing is 0. So as you go away from it, the flow becomes non-zero, but the flow at the surface is 0. So when we apply that, what we get is 0 equals b, because that means the constant b is 0. So that's your boundary condition A, and the boundary condition B is, sorry, let's use 1 and 2 because A and B are constants here. And the second boundary condition you have is a free shear boundary condition. So what that means is, on the top surface of the flow, there is no shear, or there's no traction. Okay. Again, and that is something that we can easily understand. So there's an incline, there's flow happening, and remember that in the body, in the continuum body, we can always, at any given point P, we can draw a cutting plane. So we draw a cutting plane in such a way so that the normal is in this direction. So the traction on this surface, which is a normal along x3. So this is nothing but E3, right? So the traction on a surface which is uh, traction along a normal, which is E3. So remember that sigma components are written in such a way so that sigma 1 3, sigma 2 3, and sigma 3 3 are nothing but the components of traction along on a plane which is in relation of E3. So if you have a traction here, and the traction components are nothing but the three sigma components. Now what we are saying is that it's a free shear situation. That means the traction component along the E2 direction is 0. It's like wind. If there was wind blowing on the surface, it would apply some sort of force and accelerate the flow. But there is no wind blowing, so there is no, it's a free shear. There's no shear stress on the surface. So what we say is that T2 E3 is 0. So the shear component of the traction on the surface which has a normal along E3, that's the top surface, that's how it is 0. So that means sigma 2 3 is 0. Now what was sigma 2 3? Sigma 2 3 was mu v 2 comma 3. So we have mu times v2 comma 3 is 0. So let's apply this condition and find the constant A. So let's calculate v2 comma 3 from the equation on the top here. So we differentiate that again with respect to 3. In fact, we don't need to do that. We already have that in the previous slide. So v2 comma 3 at the bottom is written as minus rho g comma mu sine beta x3 plus A. And this is 0. So that means mu times of that means minus rho g sine beta x3, oh well, x3 on the surface. So this is sorry, let me write the complete. So T2 E3 is equal to 0 at x3 equal to h. Okay, so that's on the surface of the flow. So this x3 that I've written actually is h. That means A is equal to rho g sine beta h divided by mu. Is it divided by mu? So this v2 comma 3 times mu was 0. So we do A times mu here. That's right. So A becomes this whole thing divided by mu. That's the value of the constant A. So let's substitute that. So our v2 finally, which is a function of x3, is minus rho g by 2 mu times sine beta x3 square plus rho g by mu sine beta h times x3. So we can take a few things common. So we can take rho g by 2 mu times sine beta common, and then we have twice of h minus x3. Sorry. And we already know that v1 and v3 are 0. So you can see that the velocity v2 as a function of x3 is a parabola which has a value of 0 at the surface. So if I try to plot that, I'm sorry, I keep changing the angle beta, but that's just the way I draw it. Just delete that. So the velocity is such that it is 0 at the bottom and it's parabolic with the maximum value at the top. In fact, v2 comma 3 is 0, so that means the slope of v2 with respect to 3 is 0, so it becomes 0 slope at the top. So this is how your v2 looks like as a function of x3. All right, so we see that the flow profile in a river that's flowing down an inclined mountain slope is a parabolic velocity with 0 value at the bottom. Right. So if you go down, if you dive into the river, then you would see that the velocity will go down as a parabola towards 0 value at the surface. Of course, it won't become exactly 0. That's an assumption of a no slip condition that we apply. So we saw today that we can indeed apply the equation of continuum mechanics. So the complete course was applied to a fluid flow problem today for a flow down an inclined river or a mountain, to show that yes, indeed, we can find the velocity and pressure fields using this theory. So this theory is quite useful, as we saw today. But I'll stress again that most of the practical situations we deal with, it's not as straightforward as today to solve the equations mathematically, and you need computational mechanics, which is a field called computational mechanics. You need something called computational fluid dynamics for solving fluid flows using numerical techniques. So you integrate the partial differential equations using numerical methods. So there are complete courses on how to solve this system of Navier-Stokes equation and momentum equation. You have complete courses with the name of Advanced and Basic Computational Fluid Dynamics. So if you want, you can credit those courses, which are also offered in this institute. All right, so we will stop here today, and in the next lecture, which will happen on Monday, we won't have a lecture on Monday. The next lecture will happen on Wednesday. That will be the last lecture where we'll talk about the derivation and the understanding of the energy equation, and then we'll do revision lectures on the background mathematics that we did before the lockdown period started. All right, so if there's any question, you can ask now. Otherwise, I'll see you on Wednesday.